Friends, I am here to, that's not plugged in. Oh, as usual, I'm on my tech setup, even though I'm recording. I'm here to go over some notes with you on the fundamental theorem of calculus. We started working on the fundamental theorem last class, or 2 classes ago, because last class was what I'm going to do today is do a couple more examples with you, show you some of the things that might be weird but semi-awesome about fundamental theorem. And then your job is going to be to do the practice problems. So let's see if I can make this work real quick. Because I wouldn't be me if my technology was working perfectly. All right, where's my pen? Some people would stop recording. Not me. I'll just keep going. Pen's all looped up on the wire. Anyway, hope everybody's having a good weekend, or had a good weekend. I guess you're watching this on Monday. I'm taking my son to the ear doctor, which is why I'm not joining you in class today. Okay, here we go. So, fundamental theorem of calculus. We already went through examples 4, 5, and 6. Actually, 1, 2, and 3 we did both ways. We showed how to do them with fundamental theorem. We showed how to do them with geometry. Those notes are posted. We also did problems 4, 5, and 6. We're going to do 7 and 8 together, or I'll do 7 and 8 to kind of get us warmed up, or if you want to do 7 and 8 yourself to get yourself warmed up. And then 9, 10, 11, 12 will show us some weird things, some twists, curveballs, things you might run into for fundamental theorem that might mess you up. Okay. So, fundamental theorem of calculus helps us calculate the value of the integral. The integral represents an area. We're going to look at a graph in a minute for problem 7 to show us, to kind of remind us what the area is. So in this case, it's the area between the x-axis and x cubed minus 6x between x equals 0 and x equals 1. Okay. So in the fundamental theorem process, we first identify the function in the integral, the integrand, which we like to call little f. And then big F is the antiderivative for little f. So we use our antiderivative tricks. Our backward power rule pretty much is the only trick we know right now. So x cubed becomes x to the 4th over 4 minus 6x becomes 6x squared over 2. And we'll go ahead and throw that plus c on there, even though we know, or we've talked about already, that when we're doing fundamental theorem, the plus c ends up subtracting away. All right, let me grab this guy. We have some more space. Okay. All right, so what do we do? Fundamental theorem says if you have the integral from a to b of f of x dx, that area is equal to big F of b minus big F of a, where big F is the antiderivative of little f. So now that we have big F of b for this problem was big F of 1. And that's 1 to the 4th over 4. That looks like a 14, so I gotta watch that. 1 to the 4th over 4 minus, and I might simplify that, 6 over 2 to a 3. F of a, in this case, is f of 0, which is a 0 minus 0. And technically, these both have a plus c, so that when I sit down and write out f of b minus f of a, The same thing is always going to happen with the c's. The c's will subtract away to 0. So we're going to have 1/4 minus 3 plus c minus 0 plus 0 plus c. C subtract away, and ultimately, and we have a bunch of zeros, so 1/4 minus 3 ends up as negative 11 over 4. You can do that on your calculator. You can make 3 into a fraction. 12 over 4, negative 11/4 would be the correct answer. Now, might seem weird that it's negative. Okay. That's where the graph could help us. Oops, where'd my graph go? Oh, there he is. Desmos is over on my other screen. Come here, Mr. Desmos. Okay. So if I graph f of x equals, and this is the original function I'm graphing, not with a subscript, x cubed minus 6x. Okay. X cubed minus 6x looks like this. If we were going to mark off the area from x equal to 0 to x equal to 1, oops, that's not how that scale is. Sorry, let's look at that again. I realize that's 2, so that must be 1. So that's x equal to 0, x equal to 1. It's under the x-axis. Left to right, under the x-axis. So if we were using a geometry technique, like trapezoids and things, and whatever area we would calculate, we would go, oh, this answer is supposed to be negative. So it kind of makes sense that when we actually did the work, we got a negative answer. Now, here's the fun fact. It was super important when we were looking at graphs and looking at integrals for looking at a versus b and making sure that a was smaller than b. In doing fundamental theorem problems, it doesn't matter. As long as we do f of b minus f of a, that will always give us the accurate answer. It will always tell us if the answer is supposed to be negative, that will come out negative. We don't have to really pay a lot of attention to which one's bigger than which. And I'm going to show you that. Oops, not like that. I'm going to show you that with problem number 10. I like problem number 10 because we can actually do number 10 with geometry also. My little f, or f of x, is 3x. So if I was going to do y equals 3x as a graph problem, zero, 0, 1, 1, 2, 3, 2 would go up to 6. That's what the line y equals 3x would look like. We're going 0 to 1 again, I believe. Or 1 to 0. Okay. So, yeah. So here's the fun thing. This is the area that we're talking about. This area. The integral was like that. So we were going like this. So we were going to have to think backward. And so when I calculated, I would get 3/2. But it was a backward one. Backward and above made it negative. It's a lot of thinking after you calculate the value. Not that that's bad, but it can definitely get confusing. This is why the fundamental theorem is actually better. Big F, 3x squared over 2, technically plus c, but we know it's going to subtract away. As long as I'm accurate with starting with b, in this case, b is 0, and f of 0 is going to just be 0 plus c. F of a is f of 1, which is 3/2 plugged in. Okay, because this is 3 times 0 squared over 2, and that's 3 times 1 squared over 2. 0 plus c minus 3/2 plus c is negative 3/2. I don't have to remember different rules for different combinations of numbers. If I'm consistent with f of b minus f of a, I should get the correct answer. F of b minus f of a, with big F calculated from little f, big F being the antiderivative, should be flawless. Okay. I'm going to give you other couple hints here on some of these other problems. Number 8 is just another kind of normal forward problem, nothing, or just a really normal problem. Number 11 feels like it might be weird, but once again, like I said, you don't have to, your radar doesn't have to be up for backward. Big F of negative 2 minus big F of 4 will give you the correct answer. When you do number 9, little f is x to the 1/2. When you do number 12, little f is x to the negative 2. So for both of those, the secret is going to be in figuring out big F accurately. As long as you figure out big F accurately for 9 and 12, the calculator can help you get through the rest of it. What you have to be careful about, or what you have to remember, is roots, fraction exponents, quotients, or expressions, rational functions with x in the denominator. We use the negative exponents. All right, so I've got these written out really nicely from other classes. I'm going to have all of this posted for you. Just a reminder of how fundamental theorem works. Your assignment has 7 problems on one section and then another 6 problems on another section. If you already did the first 7 and turned them in, then just do the other 6 on another sheet and turn that in. Or if you haven't done anything, you can do them all on one page and get it turned in. If you don't finish it today, I will still take it from you first thing in class on Wednesday. All right, guys. Thanks a lot. Hope you're having a good day.